Okay, so hopefully we can cover this fairly fast. So the key thing that we want you to get out of this lecture is to understand the bias variance trade-off and separately understand what an SVM is. I think the SVM part is pretty easy to go through, but if you're not clear about that, let me know. Okay, Jonathan, can you tell me why the frowny face? So if you don't mind clarifying why you're upset, that would be helpful. Is it because we don't have regularization yet, or maybe something else is bothering you? We'd like to diagnose that. Okay. So the learning outcomes this week are, again, to look at bias and variance to understand where these two sources are coming from, to make learning not occur well, and then understand how to decompose the sources of noise into these two parts. Under simple scenarios, you had a chance to practice that in tutorial this week, but also in the lecture, there was at least one case, okay? All right. So when we look at something like the fitting a target function, right? We can try to approximate it using a set of hypotheses, right? We talked about hypotheses many times already, which is basically to say a particular concept learner or a function learner in general needs to pick a set of hypotheses that it's selecting from, right? So in this lecture, we're looking at very simple hypotheses class, for example, straight lines that either have a slope or don't have a slope, right? So here we have one that has a slope. Let's see, where's my annotation? One that has a slope and one that doesn't have a slope. So you got two different choices there, right? So it's either a straight line with an intercept across or one with a slope. And so we want to know which is better, right? Better for what? And the lecture goes into quite a bit of detail about this because we are often doing two different things. We can do approximation or we can do learning. And these are two separate concentrations of different courses that we have at NUS. One is about approximation. So when we look at approximation, which is what you think about in other cases, when you're doing statistics, maybe we want to have the, a model try to fit this as best as possible, okay? And we can see here that if we use H0, it's not going to be particularly good because the best that we can do averaged out over all of the different points that we could collect on a sine curve between -1 and 1 would average out to 0. So we would get the green line that goes straight across there, right? But averaged, okay, now I used the wrong thing again. Let me see what I can erase that. Okay, but when I have it over H1, I have less error because I can sample from all the points and I can see that a good line that has a slope would work better. It approximates this curve a little better, right? So in particular, these two lines are the H bar of each of the average hypothesis that I could get when I collect as many points as I want from this, right? So I have the full power of the model to do that. Now, the difference, of course, is this word, right? So we're doing approximation here. So we have the full function and we're trying to approximate it with whatever hypothesis class we have. But in the case of something like learning, we don't have that, right? So learning, we don't get the full data set. We don't see the entire function. We only see particular data sets, right? We have our script D, right? So our script D is in particular just looking at, a certain number of points. Here we have 2 points, right? The same 2 points on both curves. And we can see what H0 and H1 is doing, right? H1 is great. It can fit these 2 points exactly because it has a slope, right? So it can go through it, both points, but H0 cannot. It has to pick a midpoint between these, okay? So it looks like H1 is doing better, but you already know the story a little bit, is that it gets worse because of something called variance, right? And that's illustrated here, okay? Our bias is basically a measure of how good our model can fit the data, in any case, okay, irrespective of the data sample that we get, okay? But on the other hand, when we think about sampling points, right, we have a specific data set in mind, right? because that's the only thing we get when we train a classifier. We have some data and we train it on that. Okay, so what we have to do is think about what's the variety of hypotheses that we would get if we are faced with different sets of data. If we see different data sets and the hypothesis that we're going to come up with are wildly different, that could lead to a source of error, right? And so you can see this as illustrated on these curves here, right? We've plotted, I think, 50 to or 100 2 points on both the H0 and H1. And we've set the best H hypothesis that we can get out, okay? So the slide that we saw previously was an exhibition of that, right? So you can see here that in particular, if you look at H1, there are some cases where the lines are really, really bad, right? They don't look at all like the approximate function that we would like to draw, which is sort of going through that midpoint line over here, okay? And that's just a function of the sampling that we get, right? So if we sample 2 points that happen to be somewhere over here and here, we're going to get a line that goes like that, right? So the variance is going to be very high. You can see that the slope and intersect of this line is very unlike the one that's represented by our H bar, which is shown in this red line over here, right? That's the case when we have unlimited data points and we sample through all data sets, then we would get a line like that. Okay, so this part about the variance is an important aspect, right? If you look at the variance of H0, it's represented by that gray area on the left-hand graph, right? So this is the area is representative of the variance, right? But on the right-hand side with H1, because the 2 data points that we sample, if we only have 2 data points, we will get very, very different hypotheses out. So while they average out better, our H bar is better, we have a lot of variability dependent on the sample, okay? And again, the sample here is only 2 points, and so that's why this gray area is very big, okay? So as this gray area is much larger than the gray area over there, it stands to reason that there might be a lot of error due just to the particularities of the data sample that we have, okay? So everyone okay with that so far? If you are clear about that, please let me know. It's important that I'm making sure that all of you are in touch with what's going on. So Akansha says, okay. Jonathan, at this point, okay. Kathy is all right. A couple of other people. How about Leslie, Chi Hong, Jess, Johnson, what? All you guys are okay? Anyone not comfortable with this? Okay. All right. So good so far. So what we are trying to say here is that learning and approximation are different, right? When you have approximation, you get to see the entire target function, right? And there are many cases in which we actually want to approximate something with something lower order. You can think about compressing data, for example, when you're sending an image over the internet and you're allowing some loss. Okay, you don't want to transmit all of the bytes, just enough to get the general impression, okay? But in learning, we're not trying to do that, right? Learning, we're saying we only have a small sample of data. We don't get to see the entire target function, and we need to learn from that, okay? So the key part here is that when we go through this calculation, you can see that the bias here is worse for H0 than H1, just because the bias is illustrated by this yellow part, okay? How much is it off on per data point, right? So if I looked at this data point here and I approximate it with the best that I can do with H1, I'll get this point here. And so my error is off about that much. Contrast that with the one over here, right? For the same point, I have a much higher error rate, okay? So my bias is worse. You can see the yellow area here is a lot smaller than the one over here, okay? So that's why these numbers are the way they are, okay? But when we go to the other part, right? When we're going to the other slide, right? You can see that the variance here is a lot larger, okay? So we have to add up all of these points and then we can get a measure, okay? So we can take the sum of these two terms and see that actually the variance is the killer part when we go to H1, okay? It's not to say that lines are bad, right? It's definitely just a case that we've artificially restricted the number of points that we get in this data set to just 2, so that we can get a very simple analysis of this bias and variance problem. Okay, so here, all we're trying to impress upon you is this idea between bias and variance, which is to say that we need to fix the model complexity of what we want to learn, whether to use H1, H2, or a very large complex model like a neural network, or something that has lots of fitting, such as a decision tree, when we need to match it to the data resources that we have. Okay, so the data resources in this case, we were actually just talking about quantity because we only have a certain number of points. But often we also have to think about quality, right? Quality means whether the data is acquired in a noisy fashion. For example, you have a measurement sensor, but that sensor is off in a Gaussian distribution way, or it has some other type of bias, okay? And so that information needs to also figure into how much you trust the measurements in your data to determine whether to set a good model complexity or not. Okay, so you don't want to try to think too much about the target complexity. We're looking at this thing and you're saying, well, that doesn't look like a line at all. It's a sine wave. So it looks like it will be a lot better to think of this as a line with a slope, at least on this interval of between -1 and 1, right? We have to ask ourselves not only what the target function is, but more importantly, what type of data are we getting to and understand that function, okay? All right, so overfitting, right? So this is the first part where we're looking at a simple target function with only 5 points, okay? So if you have a 4th order polynomial, it can go exactly through 5 points, right? So that will have no training cost because you can fit it exactly. But if you get any another 5 points from here, let's say this point over here, this point, and maybe these 2 points over here, but don't measure exactly because it's slightly noisy, then we're in a lot of trouble because we won't get this nice smooth curve. We'll get something that might jag up and down, like something like that, right? So that's going to be terrible because everything off of this line, okay, off of this line is going to be part of the error from the variance, okay? So we do have to worry about those parts, okay? And so that's exactly what you see on the next slide, right? All of these parts that have gone from the red to the blue line, they're errors in our fit. And that's the big problem, right? What we want to make sure is we fit the data that's provided to us, but don't fit any other sources of information. And the problem here is that we can't determine whether what we're given is real data or it's somehow noise, okay? So we need to make sure that we fit the data no more than is warranted, just enough, okay? Because when we fit the data too well for a number of different reasons, okay, it can be harmful. Our generalization when we get to the actual target function, but draw new test samples is going to be fairly different. Okay, so that is the key part of overfitting, and it is one of the most important lessons that you can get out of machine learning is that we need to make sure that we have a class of hypotheses, okay, that suits the type of target function we want to get. So even when we were talking about concept learning, we said we're going to imagine that your drink categorization of your friend can be represented by conjunctions of constraints, okay? So if that actually models the data well, that's a perfect hypothesis class because the unrestricted set of hypotheses is very large, right? So we don't want to mess with that power set of possible hypotheses that we could get. We want to restrict it to a certain size. And that's exactly what we want to do when we cure overfitting, okay? So let's take a look at another example. Here's a case of a 2nd order versus a 10th order polynomial, okay? So we can choose either to use H2, right, our H2, or H10, okay, to represent this, okay? So here we have this is an actual function. This function is a 10th order polynomial, okay? But it's got some noise. As you can see, it's got some wiggle off. These points were measured, but they're not actually on the right line, okay? And you're given 15 data points. And now we want to discuss whether we are going to choose H2 or H10 for the answer, right? That's what we want to do. And the same, we can think about another F, okay, let's call this F prime, which is a 50th order polynomial, and it's noiseless, right? There's no noise in it. We measure the points exactly. All of these points are actually on the line, and we want to ask the same question, right? So hopefully you're getting an idea about this, right? So if you pick your model, let's do this with you, okay? So for the first model, which one do you think will work better? A second order or 10th order? Given you already know that you need 15 data points, right? So if you say second order, give me a yes, okay? If you say 10th order, give me a no on the participants list, okay? So maybe I'll select a 10th order for the first one, okay? So all of you are choosing a low order polynomial. Okay, this is a 10th order polynomial, right? This is in the class H10, okay? So why don't I use H10 to represent it? Because, well, maybe there's noise, but there's no way something like H2, which is a simple parabola, right, is going to get anywhere close to fitting the target function, right? I mean, it's got 10 orders of 10 coefficients, right? H9 all the way down to, um, uh, an intercept, okay? So I guess you can see where we're going with this, right? Because here, in the case with a low order polynomial function, our H2 will at least go through the middle parts, right? It may not get any of the parts right at all, okay? But the waviness, as you can see from the 10th order polynomial fit, won't be there, right? So all of these really, really bad parts, where it's really high or really low, they'll be absent, right? So even though there's a lot of error on the actual curve, from the green line, it's not going to be as bad, okay? And that's even true too for the higher order polynomial, right? Here we have a 50th order polynomial, and it's noiseless. So we can try to do it with the 10th, and it looks like it did pretty good job on all of the points that it got, right? So it went through all of these 15 points pretty well, okay? But the problem here is, again, we're not just looking at those points, right? We're looking at the test data, which is not revealed to us, right? And those, you can see, again, the tails that go off the charts over here are likely responsible for the high variance, okay? So that's no good, okay? So again, we're going through the same concept ahead of again and again, right? So both of these cases in this slide, right? We have two learners, right? An H10 learner and an H2 learner, and both know the target function is 10th order, okay? Exactly the same. And you get 15 data points, and we end up with the same problem, right? We see that in fact, the second order is going to win again. And this is because of one thing, okay? What is it because of? Is it because of the number of data points, or is it because of the target function, okay? So let's take a look. If you think it is because of the data points, give me a yes. Or if you think it is because of the target function, give me a no, okay? So this is no, this is yes, okay? Meaning that if we had more data points, maybe we'd get a better fit, okay? Or if we lowered the target order to something else, okay? Or expanded it to a higher order, maybe it would get a better fit. Okay, so all of you are right on the ball. Yes, it has to do with the number of data points, okay, that is causing the overfitting. So when you think about this in your own projects, especially if you're doing deep learning, this is a very common problem, all right, that people like to use or implement or try deep learning models that may have been good for a very large data set or require lots of synthetic data, okay? So when you try a deep learning model, you should also try to do this. Restrain the model, okay, so that you don't overly do too much fitting, right? Because if you fit all of the data perfectly, you get very low training data error. But when you get the new data that's from the testing data, it will overfit, okay? It will show wild variance because it's not drawn from the same distribution. Oh, sorry. Rather, it's drawn from the same distribution, but your learner has fit the particularities of the data rather than information that's generalizing beyond the training data set. Okay? All right. So let's go on. Okay. So we come to the support vector machine. So this is a really easy thing to understand, is that when we talked about the perceptron, right, there was basically the simple idea of finding any hyperplane that fit between the 2 points, right? So we could have drawn a point like this, you know, something like that, okay, or maybe something like this, and there would be no distinction between them, right? The perceptron just finds something that separates the two classes and it's done, okay? But when we think about this problem a little bit more acutely, right, we can think that there's a line that might be better than the rest of them, okay? In particular, when we think about the lines that are closer to one of the sides here, we might think that's not a particularly good line, right? Because it doesn't leave a lot of space for creating leeway between the two sides, okay? So if we draw a hyperplane that sits squarely in the middle of the divider between the positive and negative points, then we get a highway in some ways that's maximally wide, okay? And then we've talked about this before. This part is called the margin. Okay, this just basically divides a positive class from all other negative classes. Okay, if you're doing multi-class classification, that's how you would think of it. Okay, so in some ways, it's very good to have a fat margin or a wide margin. Maximize this margin as much as possible, so that if we have measurement errors on any one point, let's say this point was not exactly here, but somewhere in this circle, say there's some Gaussian noise in the measurement of its x and y, we'd still be safe, right? Because we didn't draw the line so close to the edge here that it would possibly be classified on the wrong side, okay? So that's the idea behind this. And the nice thing is now you have the idea, the intuition of capturing a optimal or unique hyperplane, right? So it's very easily defined. You can just find the points that are closest to the decision boundary that would nicely separate two things, right? And then say, okay, well, I'm going to draw a line that's going to be able to look at the perpendicular bisector between these 2 points and cut it in half, all right? And I'm going to define the distance between these 2 points as a unit distance, okay, 1 and 1. And so I'm just going to put that hyperplane right there. Okay, and there's interesting math to solve this equation, and we used to teach it in previous versions, but because the linear models part was too filled and the derivation is just more mechanics, we didn't go through it this year. Okay, so the only thing that you need to take away from the support vector machine is it gives you a intuitive, unique solution to finding a hyperplane. Okay, the problem with finding the SVM, as it is with many other things, is actually calculating it requires some type of linear optimization. Okay, so it requires quadratic programming or QP, which you might learn when you go to you know, optimization theory and things like that, which requires a lot of computation. It requires a cubic operation, and so this is not that easy to do mechanically. Okay, you have to actually go to a library and run a couple of different algorithms, some that are quite sensitive to memory, to try to approximate and find a good solution to the quadratic programming problem here that allows us to get this done. Okay, So the one thing that we will say about this that I also alluded to in today's email, some of you may have gotten the email already, some of you will get it probably tomorrow, is that there is very, very beautiful math behind the support vector machine, in the sense that when we compute these points, okay, and we try to figure out how close they are to each other, they require something called a kernel function. Kernel function. I'll just write this out. You don't have to remember this because it's not examinable. I know you guys are interested in that, okay? And a kernel function is just something that takes one point and another point and computes a similarity, okay? A distance, okay? So I can say, for example, 2 points are similar if they're close by, okay? So in some type of vector space, maybe we'd say that 2 points that represent vectors, they're similar if the angle between the two vectors are quite closely aligned. That means the cosine between the two, okay? And this is something that you may have learned already if you took our information retrieval class, but you know, in vector space, that's how we would calculate similarity, right? So some type of distance measure about how close two vectors are to each other. Okay, so this type of kernel function, this similarity function, is something that you can design. In other words, we can design whatever type of function we want to measure whether two things are similar or not. Okay, it's not governed by any particular math. We just have to satisfy some criteria, namely that it must be a positive semi-definite comparison function. But basically, we can design what this kernel function looks like. Why is that cool? Is because when we have a kernel function, we can think about what type of data we're trying to compare, right? If we have two images, we might say, well, let's think about what an image is when we say it's similar to each other. Okay, maybe the middle pixels need to be more similar than the side pixels, because when we take pictures, we tend to focus on the middle region. When we think about natural language processing, we might look at keywords or, for example, the syntax tree of an utterance or a set of words, and design a kernel function based on that. And it turns out that kernel functions are generalizable to quite a lot of things. In fact, you've probably already noticed that something like K and N can be using kernels, right? I mean, K and N, you have this thing that says, what's the distance between 2 points, right? So there's a kernel function there too. And you can then say, instead of using Euclidean distance for K and N, let's use a kernel function. Let's measure how similar to time series, to Pokemon, to, I don't know, news articles, to headlines, to social media posts, how similar they are to each other. And then if I design this kernel function, I can plug this kernel function into several different learners and have it take effect. In our sports car analogy, we would say the kernel function is an engine, okay? That type of engine can be swapped out, and you can put another engine in, another kernel function into your car, into your learner, and it will do different things. It'll do different similarity computations, okay? So that is the really, really cool thing about kernels that we can use in an SVM. And the way we use it in an SVM is then it's going to change the way we think about these points. It's going to map these points to a nonlinear space, okay? Which is why we said kernel functions can often be looked at very differently than what you see in a normal SVM picture. So let me bring a picture of an SVM down with you. For you, let's say SVM, kernel, okay, and if we look at pictures of these things, right, you can see what they do, right? So here is an example of that. We have an actual picture of the linear classifier. This is in our Z space, okay? But because we applied a kernel function, we mapped all of these points into a new space, our Z space, where our kernel function is actually making the decision of where things are close to each other. And in this kernelized space, we have this wavy line here, which is actually a straight line in the Z space. So this is, again, our X space, right? Our X space here. Yeah, X space, and this is our Z space. And this is afforded by our kernel function. We can take these things, put them through our phi function. which is, or phi function, okay, both pronunciations are fine. And this is basically our kernel, right? So we're using a kernel function from x and x double prime, 2 points, and then saying how similar they to each other, and then using them to map them into this space. Okay. All right, good. So let's get this off of here. So one thing about support vectors machines is, I said, it has these things called support vectors, right? The support vectors are basically points that support the hyperplane, right? We're just saying that all the positive points have to be above the hyperplane, you know, have to have a result larger than 1. And all the points below the hyperplane are negative points. They have to have a result less than 0. And we're just fixing the distance between these two as positive and 1 for each, okay? So that's why we said when we move it into the Z space, we have this really funky shape, right? Because we are mapping it using a nonlinear mapping through the use of a kernel function, okay? Now, in soft margin SVM, it's just a little bit more complicated, but not much more. We still want an optimal hyperplane, but we want one that can consider some noise, okay? So noise here would mean thinking that perhaps this point isn't so good, all right? Because we can see the collection of blue points all over here, and this one might actually have been labeled wrong. It might be a red point, okay? If we were to draw an optimal hyperplane that separates things neatly, we would have something like this. But if we say maybe we allowed ourselves to knock down or classify this as a red point, or say there's some error with it, maybe we could draw a wider highway between the points, something like that, okay? So if we wanted that and we wanted to say that perhaps our data set has some noise, we don't trust, like in the perceptron case, we want to be able to handle misclassification in a variated way, we can deal with that, okay? So the way we do this is by using the concept of error, okay? Error on an individual point. So we're gonna say for each point, each of these points out here, okay, we are going to associate an error variable with it, okay? This xi variable, okay? So that means for each point, how much was it off by, okay? And if it's off by nothing, then we're all good. So all of these points over here are fine. All of the points down here are fine, okay? It's just the ones that happen to land in the middle of this yellow road, okay? For example, this one here, that has some type of violation, okay? And we don't like that, so we want to try to find a hyperplane boundary that tries not to make errors, okay? But when we does have some errors, we're going to accept that, but we're going to add a penalty, okay? The penalty is basically how we operate in a lot of things in machine learning, right? If we don't like something, we can penalize it, but we'll let the machine optimization decide how bad that is, right? So we can decide, okay, are we gonna penalize this a lot or a little bit? It turns out for SVMs, the formulation that we have is a linear penalty from where it should belong. It should belong somewhere on this side of this line, right? Because we said our margin is 1 here. Our margin is 1 here, okay? It's an arbitrary unit of measure, but anything lying on the highway itself or on the wrong side of the highway would be considered incorrect, okay? So here we have some error, okay? And so we want to penalize it from that. How can we, okay, Chinghan asked, how do we set error parameters in the model if we can't visualize the data? That is a good question. So many times you don't need to visualize it. You just have to do some error analysis on your own about whether you think the error that you're observing is acceptable or not, and with what tolerance, right? So here, when we visualize the data, we can see that it's actually sitting close to the hyperplane. It's still correctly classified as a negative point here, okay, if we think of the blue as positive, as negative, okay? It's just that it's lying within the margin, right? It's inside of this highway. So it's, you know, we would like it to be moved out of the margin so that it doesn't have any violation of being in the margin, okay? So this is actually still gonna get us good classification, but it messes with the spacing of the hyperplane if we let it sit there, okay? So that's why we have a penalty, okay? Okay, so Akansha didn't understand this slide, so I'll try to go back to this again, okay? So when we are thinking about soft margin SVM, okay? The soft in this case comes from the word, the tolerance, okay? The tolerance of some type of error, okay? Because what happens here is the perceptron and SVMs by themselves, or hard SVMs, as we introduced before, don't allow any error in the data set. Red points must be red, blue points must be blue, and when we find a separating hyperplane, we have to make sure that the red points are on one side and the blue points are on the other, okay? That's what we mean, okay? When we come to this slide and we say we want to allow some error, okay? It means that we allow our points to possibly be incorrectly classified and still have a classification boundary, or we allow them to violate our margin. Our margin is, again, this yellow stripe, okay? You can think of this as a highway, right? So we don't want obstacles on our highway, so we want to move them off, okay? So if we were to actually do a hard SVM on this slide, what we would say is we would probably draw a line like this, okay? Because the left side of the highway would be here and the right side of the highway would be here, okay? And you can see that this highway over here doesn't have any points sitting inside of it, okay? That is to basically allow the margin, okay? So that there's space for other points that are incorrectly measured to fit there, okay? So that is a hyperplane that would generalize well, okay? So in this case, when we are building a soft SVM, okay, what we are saying is that we want to build a large highway, a wide highway, right? Because we are doing this, what we say is max margin, okay, trying to get a hyperplane with large margin so that we can generalize better, okay? So if we try to build a large highway, sometimes we will have data points that fall inside of the margin, okay? So we've got this data point over here that is unfortunately violating our margin. It's on the yellow line, and sometimes, you know, you might actually have a blue point over here, which would be a very bad violation, right? It's completely on the wrong side of the highway, okay? If we have things like that, we can still try to build a maximum marginal highway like this, but except that some points are going to have error, okay? So this is what this is quantifying. This term is a term per point. So for example, this term, this point and this point will have a non-negative error, okay? And what we're doing is we're going to sum up all of the errors over all of the points to induce a total fine, okay? If you build a highway this wide and put it in this position, you're going to have to pay whatever penalty is represented by these 2 points, okay? On the other hand, if you built a highway that has no penalty, like one that goes through the lines that I showed you before, ones like that, okay? You'll build a narrower highway, but your margin won't be as wide, okay? When your margin is not as wide, then you have harder problems with generalization, right? Because again, it depends a lot on which sample of data you pick, just like we talked about in the previous part of the lecture on bias and variance, okay? So we want to generalize well. When we generalize well, we want to get a large margin classifier, okay, in linear models. And so that's why we want to find the correct positioning of this support vector hyperplane, okay? Is everyone clear about this? Okay, so a couple of people are not very clear about what we mean by having a larger margin, okay? The larger margin allows us to have a more general model because it accepts some error, okay? So if we say that these points are just somehow aberrations in our data, okay? We can draw a larger margin, okay? And that allows us more flexibility, okay? So here's a slide that explains that, right? So if we, let's say, have these same 4 data points as I drew over here, okay? And you can see how these different hyperplanes are being drawn, okay? So the middle line is the actual hyperplane. And then when we try to extend that hyperplane perpendicularly from the left and the right, or from the top to the bottom, whichever way you want, until it bumps into one of the data examples, that is the margin, the width of the highway that we're inducing, okay? And so why is this better generalization is over here, okay? So when we have the case where we have data that is noisy, we can cater for more noise in our measurements when we have a larger margin, right? If we have a margin like this, our classifier isn't very robust, because as soon as we get a data point like this and it was measured just a little bit off, then it's on the wrong side already, okay? When we have this particular hyperplane here that maximizes the total margin between the red crosses and the blue circles, then we are guaranteeing that even if I measured these points incorrectly by a lot, okay, by up to any part in this gray circle, okay, I will still get the same answers for my data set, okay? So basically we're trying to handle noisy data and also lessen the dependency on the actual data itself, okay? You can see how in this case, we have a lot more variability about where to place our hyperplane, right? But in many ways, it depends on which data point we got, right? If we didn't have this data point here, we might get a very different answer, okay? Imagine if we look at this case on the right-hand side, even if we didn't get this data point, because we have fat circles, this particular hyperplane won't get changed as much, okay? It doesn't have as much wiggle room as a small hyperplane like this, which would have less margin. Okay, so I hope I answered Li Shuo's question about that and helping other people understand this. So Chinghan, I hope I answered your question, but if not, please.
Thanks, bro. Actually, I just thinking this is could be basically a trade-off question here, right? So you have more margin, then you may wrongly classify some data point as well, and that's so. Is how to find the balance in this two? You like say first example here, you can classify the red one near the line as a wrong, then you can much bigger margin, right? But actually that one you classify wrong, so your accuracy dropped here. I mean, at least in the training data here. And you want to use the testing data to see that that would there be some data leakage concern as well. So that's I think the trade-off here is a bit
Yes.
challenging.
Yes,
Yeah.
exactly right. So there is a trade-off. So Chinghan just said, what happens if we think of this as a noisy data point, right? Then I could just ignore this. And I could just think of, you know, between here and here, I'm going to draw the midpoint. And so I get a huge margin, something like that. And that's acceptable in certain cases. We might say we want to have an even larger margin, okay, and accept more classification error. And in this soft SVM, we handle exactly that case, okay? So the way we do it, as it says here, is we're still going to find a separating hyperplane. Okay, this is our signal times the observations and our weights. Okay, and here's our normal linear hyperplane. But in certain cases, we're going to accumulate error for points that we are saying we're okay if it didn't come out exactly right, not on the margin, somewhere in the margin, or even misclassified on the wrong side. Okay, and the way we do this is by quantifying this trade-off. Okay, the trade-off that Chinghan just mentioned. Okay, so that is with this parameter C. It's a tuning parameter. It's a hyperparameter that you can say that says how much do I want to accept errors. Okay, so you can see here, this is the same data set. You can see the same points here. But if I draw a wide margin, for example, on the left, okay, I can get a wider highway that might have more generalization capability, but I'm going to have more things that are wrong. Okay, now if I go with the classifier on the right, okay, this is not bad either. It's just got a different C. Okay, the C here says that I don't like errors as much, right? Because we're trying to minimize this. This is our loss, okay? This is our training loss, okay? So we can either accept penalties, higher penalties when we have violations, okay, which is why you can see here there are many less violations than on this case, all right? So all of these points here, even though they're on the right side of the hyperplane, this is the red side of the hyperplane, they have a loss because they're sitting on the highway itself, okay? So all of these points have some loss, okay? It says here xi is greater than 0, xi is greater than 0, okay, for all of the things that's sitting on the hyperplane or on the wrong side, like this one is definitely classified wrong. That is going to be classified by the support vector machine as a circle, even though it's an X, okay? So what we're trying to say here is that if you look at this data set, okay, if we are going to think that the data set is correct or that we want, more dependency on the data set itself, okay, and we expect all data sets to be drawn similar to this one, then maybe we would have a high penalty for errors, okay? We don't want as many errors. We want something closer to a hard SVM. But if we believe that when we get more samples of data, they're going to be quite varied, okay, in the sense of bias and variance varied, that we would actually get problems with this, all right? That then we would try to set something with a lower C so that we will allow a larger margin between points, okay, on the left and the right, but accept errors, okay? So this is a nice way of dealing with the idea of not needing something as rigorous as a perceptron in making sure that you have things that are linearly separable, right? So here we handle those two cases, right? So you can think about why that's important, right? If we have things that are more or less separable, like you can see this case here, all right? Most of the points that are red are closer to the origin down here, and most of the ones that are blue are closer up here. Then we could say maybe, you know, even though there's errors, I don't want to try to draw a line that looks a little bit like this in order to get all the data samples right. That would just be too much, okay? We don't think that's correct, okay? So maybe we will just accept the fact that we believe that some of these points are maybe measured wrong or have the wrong label, okay? So we accept the fact that there might be some error. So this is a case of slightly non-separable data, okay? This is the target of why we have something like soft error, okay? It's an error that allows you to penalize, but doesn't completely forbid it from happening, okay? You're allowed to have error, it's just it comes with a cost, okay? On the other hand, if we have something like this, okay, if we were to use a single line, there's practically no way we can get it. And we have to deal with this in other ways, right? So that's why we say maybe you want to use a nonlinear transform in these cases, okay? When we can see that the error would still be huge, even if we allowed soft margins, okay? So I hope that clarifies a little bit of this part to you. Okay, so let's finish up the SVM. Okay, so you'll see this in other places as well, okay, that we have this trade-off, okay? So we had this term that, we had this term over here, right? Where we had a term for tolerance of errors, okay? Again, this is summed over all the points that could be misclassified. And then we have this term, which is basically placing the hyperplane, okay? With respect to maximizing the margin. So this term is to maximize the margin. Okay, I'm not going to go over the math for that part, but that's basically what it's trying to do, okay? And this part is to minimize the soft error, okay? And so when we see this going around, we can set different levels of C to say, how much do I hate errors, right? If I'm definitely sure that my data is correct, I don't want any data error, then I can set either a very large C, which means don't forgive errors, or pretty much, you know, in the hard margin case means it must be linearly separable. I don't allow errors at all, okay? So this still allows errors, but you have a large penalty on this, okay? So then you have to look at the type of data that you have and decide, okay, how much do I trust this data? How much do I trust that the variability of the data isn't going to change a lot with different samples, okay? So in the bias variance part of this lecture, we said earlier, that is a problem, right? If we only have we have something complicated like a sine wave, and I only get 2 data points from it, the 2 data points that I'm going to end up with are going to come up with very different ideas of what their best hypothesis is, okay? And we need to control for that. All right.